you what to expect today. At the end of the hour, I want to again review your course selection options for next year. I think most of you got some of those options explained to you at least briefly last Thursday. I also want to talk about the end of the semester and beginning of the new semester, and we'll do that after we complete this presentation. Today our focus is going to be on reviewing what you already know about percent composition. That's how I'm going to start with just a simple example of calculating percent composition, and then we're going to show you how to determine empirical and molecular formulas for compounds using percent composition. How's that sound? That sounds like good stuff, huh?
That sounds amazing, sir.
All right, awesome.
Wow.
Let's get you up.
Really?
All right, so on your note-taking sheet on the top left, the first thing you want to do is just quickly review how to do percent composition. This should be review. It should be fairly simple. With percent composition, the first thing we want to do is determine what, well, for percent composition, we're going to take the part and divide it by the whole. So we want to find out how much mass magnesium, what percent of mass of magnesium carbonate is the magnesium, and which percent of it is carbon and which percent of it is oxygen. So the first thing we're going to do is find the molecular mass of that compound. We've done this many, many times, but we'll do it again one more time just to remind you. So you're going to refer to the periodic table. In the chemical formula, you'll see that there's 1 magnesium, 1 carbon, 3 oxygen. So we're figuring out our molecular mass. We count magnesium once, 24.31, plus the carbon, which only shows up once, 12.01, plus the oxygen, and there's 3 of them, each of them at 16 grams apiece, for a total of 48 grams for the oxygen. When we add that whole mess together, 84.32 is the molecular mass of magnesium carbonate. So that's our whole. By no means do you have to wait for me if you know what you're doing here, but when we find the percent magnesium, then we're going to take that value that we determined contributed to the total mass of magnesium carbonate, 24.31, and divide it by the total mass, 84.32. And then we multiply that by 100 to get it into percent form rather than decimal form. And we've got 28.83%. And then you can go ahead and do the same thing with the carbon. And the oxygen. And of course, if we're figuring out what percent each of these is of the whole thing, when we add each of them together, it should all add up to 100. I'm going to encourage you, remind you, tell you that as we're going through this process, you should continue to at least record to 2 decimal places, and in a lot of cases, it might be a good idea to go to 3 decimal places. If we were to round, say, magnesium to 24.3, and carbon to 12, and oxygen, there's not much rounding to that, 15.999 already. But we might find that those percentages only add up to 99.8, or if we rounded the other way, it might be 100.2 or something like that. The more decimal places you go out, the more successful you're going to be. All right, so that's percent composition. That's a review. That's what we already know how to do. Now there's 2 types of formulas we're going to discuss today, the empirical formula and the molecular formula. The empirical formula, at least in terms of chemistry, definitions is the simplest whole number ratio of the atoms in a compound, or the lowest ratio. So your subscripts in your chemical formulas for the empirical formulas are going to be as small as they can possibly be and still be whole numbers. We'll never have fractions. It'll never be H 2.503 or anything like that. All of our subscripts will always be whole numbers. But the empirical formula will be the lowest possible ratio. The molecular formula is the one that tells you the real story. This is how many of each type of atom are actually in the molecule. And that's the only one that you've seen up to this point. We haven't done any percent composition type calculations up to this point, so we've always just given you the formulas. Anytime you are given a formula, H2SO4, that tells you the molecular formula. But in the analysis in the lab, there are going to be times where we would calculate what's the empirical formula and then use that to ultimately determine what the molecular formula is. So another expression for the relationship between the empirical and molecular formula, the molecular formula is going to be the empirical formula multiplied by some number. A lot of times that number is just going to be 1. The molecular formula and the empirical formula can be the same formula. But sometimes the molecular formula might be 2 times as big as the empirical formula, or 3 times as big. I'll give you a couple of examples here directly. Here's one. If your molecular formula is C6H6, that tells you that there really are 6 hydrogen molecules, or hydrogen atoms, bonded with 6 carbon atoms to form that molecule. But as you can see, if there's 6 of each, it's really a 1-to-1 ratio multiplied by 6. So your empirical formula for C6H6 is just CH. As I just mentioned a few moments ago, the empirical formula and the molecular formula can sometimes be the same. For ionic compounds, they are always the same. Ionic compounds are always given in their lowest ratio. A couple of examples: sodium chloride, 1-to-1 ratio; magnesium chloride, 2-to-1 ratio; aluminum sulfate, 3 sulfate ions for every 2 aluminum atoms. But still, there's no way that we can simplify those subscripts down to smaller numbers without going into fractions, and we don't want fractions. For molecular formulas, again, they might be the same, but many times they're not. And a couple of examples: water, H2O, can't be simplified down any further, so the molecular formula and the empirical formula are going to be the same. The next one, you have C6H12O6. We could divide each of these by some number and get them all smaller. We could obviously divide them by 2, 3, but to get them as small as we want, 6 is the way to go. So for every carbon atom, there's 2 hydrogen atoms and there's 1 oxygen atom. And the last one 11 and 22 could be simplified, but that 12 messes things up. So we can't find any number that will accommodate all three of them. So that's going to have the same formula both empirically and molecularly. So hopefully you think that concept itself is easy. Next, now that we know what an empirical formula is with respect to a molecular formula, we want to be able to determine the empirical formula. So there's a three-step process. Here's what we're going to do. First thing we're going to do is assume we're always starting with 100 grams. And typically what you'll be given in a problem is the percent composition. So if something is 60% carbon and 40% oxygen, those percentages add up to 100. So if you assume you're going to start with 100 grams, you would just start with 60 grams of carbon and 40 grams of oxygen. And we'll go through that example as soon as we talk you through these three steps. So we're going to start with 100 grams, and we're going to find out, determine how many moles of each element are in that 100 grams. So I got ahead of myself a little bit here. Once you determine how many moles of each element you have, you're going to take the smallest number of moles that you found and divide that into your other values. And obviously your smallest number divided by that smallest number is going to give you a ratio of 1, but all of your other ratios are going to be bigger than 1. They might be whole numbers in all likelihood. They probably won't. It might be 1.5, it might be very random numbers, but once you divide them by that smallest number, most typically you're going to end up with halves or thirds or maybe quarters in your numbers, and then we're going to come up with one number that we can multiply by all of our ratios to get them all into whole numbers. So you're going to multiply each number by an integer. This is going to be the same integer that you apply to all of your values from step 2. Hang in there, buddy. All right, so the example we're going to go through is listed right below those three steps. Adipic acid, as I said, very commonly you'll be given the percentages of the composition. So this tells you that 49.32% is carbon, 43.84% is oxygen, and 6.85% is hydrogen. All those percentages add up to 100. So if we assume that we have 100 grams of adipic acid, 49.32 of those grams would be in the form of carbon, 43.84 of those grams would be oxygen, and the 6.85 would be hydrogen. So wherever you see a percent sign, you're going to replace it with grams. So we'll start out with carbon, 49.32 grams of carbon. And we do the one-step conversion to get those grams of carbon into moles of carbon. And by all means, if you know what you're doing at this point, you don't have to wait for me. You can go ahead and convert your grams of oxygen into moles of oxygen and your grams of hydrogen into moles of hydrogen. Bless you. Once you've done that, because we've got 3 different elements in that compound, you're going to have 3 different mole values, one for each element. And this completes our first step. Assume it's 100 grams. Find the number of moles for each one. Next, we're going to identify our lowest number. We get 2.74 moles of oxygen. That's less than the other 2, so we're going to divide each of these 3 numbers by that smallest number, and that will ultimately give us a ratio that's going to tell us that for 1 mole of oxygen, we're going to have this many moles of hydrogen and this many moles of carbon. So for the first one, 4.107 divided by 2.74 gives you 1.5. That just simply tells you that there's going to be 1.5 moles of carbon for every 1 mole of oxygen. You need to back up, Nick, or are you good? Same thing with hydrogen. And this gives you 2.47. If we carried these digits out a little bit further, I mentioned earlier, don't get all loosey-goosey in your rounding, don't round too much or too often. If we had carried out more digits here, this would be closer to 2.5. It's pretty darn close to 2.5 as it is. And so we're going to assume that that's 2.5. If it was 2.4 or 2.41, then I think I should go back and double check my calculations, or at least try it again with more digits. But if it's 2.49, 2.47, that's pretty much 2.5. And then finally, 2.74 divided by 2.74 is not 1.5, it's 1. So don't write 1.5, it's 1. Promise. Not 1.5, just 1. And that's step 2. So our last step is to identify one number that we can multiply all of these by so that they'll all be whole numbers. If we got halves, something and a half, 1.5, 2.5, then we can double it and we'll end up with whole numbers. If we've got something that's 1 1/3 or 2 2/3, multiply the whole thing by 3, and that'll get us to a whole number. Quarters, of course, you want to multiply by 8, by 4, sorry, not 8, by 4. So, carbon, hydrogen, oxygen, if we multiply each of them by 2, we're going to end up with whole numbers. So 1.5 times 2 is, of course, 3. 2.5 times 2 is 5. And 1 times 2 is 2. And we do that because we have to have whole numbers in our formulas. So those are going to be the subscripts for our empirical formula. That's going to be the lowest possible ratio of that compound. C3H5O2. That may or may not be the actual molecular formula. Well, how could we possibly know? Well, whatever this compound is, we could experimentally determine what the molecular mass is. In this case, we're going to give it to you. We're going to tell you that the mass of adipic acid is 146 grams per mole. So we use our empirical formula and our molar mass to figure out what the real formula is, what the molecular formula is. And this is going to be simple math also, just a case of following the progression. So we got 3 steps again. The first step is to simply find the mass of our empirical formula. So what's our empirical mass? We got 3 carbons multiplied by 12.01 plus 5 hydrogens, 1.01 apiece, and 2 oxygens at 16 apiece for a total of 73.08. So at this point, you might just be blindly following my lead and writing down whatever's on the screen, or you might also be processing what's going on. But if you're looking at the empirical mass and see that it's 73 grams, and the actual mass is 146 grams, you should see that it's half of our molecular mass, which might make you think that the actual formula is going to be twice as big or double what our empirical formula is, because our actual mass is twice as big as our empirical mass. And that's exactly what we're going to find out. So our next step is simply to take our total mass, our molecular mass, the actual mass, and divide it by our empirical mass, to find out how many times bigger the real mass is relative to our empirical mass. As we just said, it's going to be twice as big. And once we've identified that, we're going to take that 2, twice as big, and distribute it through our empirical formula to get our molecular formula. So we're going to have C3H5O2 all multiplied by 2. There he is. So earlier on, we had the formula in parentheses with the little n as a subscript outside the parentheses. We just figured out what n was for this particular compound. I don't think any of that is difficult math. It is a couple of steps to get from the beginning to the end. And hopefully, as we were talking through this, the steps have some purpose to them, some sense to them. If it doesn't the first time, after a couple more repetitions, it'll make more and more sense to you. But for the time being, it can be just like math homework where they show you how to do it, and then they ask you to do it again and again and again. Any questions on what we did? Okay, giddy up then. We're going to transition. That's the end of what I got here. We're going to transition from this to your homework and talk about course offerings and end of semester, beginning of semester.
You're getting more choices, like to get less conflicts, because now like so where last time I don't have it. There's never going to be like the same classes we have some days might have conflicts. Yeah, it's like if there's like you can't take one step credit.
Okay. Just a slight detour real quickly. I think most of you have already seen most of these options, but just to give you a quick refresher, a quick overview of what your options are. You've just taken chemistry, or you're in the middle of it, you haven't killed the beast yet, but you are in the middle of chemistry. Next year, AP Chemistry is certainly an option for you. Downside of AP Chemistry is that you don't get to see Mr. Neubauer or myself on any given days. It's all Mr. Gussie. The upside is that you get to see Mr. Gussie for all of your classes. So he's running that AP Chemistry show. That is an index course. If you don't know what grade indexing is, on your GPAs, if you got a 4.0 right now, let's just pretend you get a 4.0 right now, and you get an A in chemistry, you're going to keep your 4.0. If you then take AP Chemistry next year and get a 4.0, you get more than 4 points. You get 4 times 1.025. So it's a way to actually get your GPA above a 4.0. Or if you're a little bit below 3.88 or something like that, you could potentially bring it back up to a 4.0. So you can earn a little bit more than your other courses. So they're scaled by 1.025. AP Biology as well. Obviously the prerequisite for AP Chemistry is you have to take chemistry first. Prerequisite for AP Biology that's taught by Mrs. Wirtz is biology. That's a required course, so you've already got that under your belt. AP Physics 1 is an option. Each of these first two are the equivalent of one semester or 1 year of introductory college chemistry or biology. AP Physics 1 is the equivalent of one semester of an introductory college course. There is no prerequisite for AP Physics 1. If you're interested in physics, you can take either physics or you can take AP Physics 1. AP Physics 1 gives you the chance to get your grade indexed, and all these AP courses then give you the opportunity to do well on the AP exam and test out of that first year of college chemistry, biology, or the first semester of college physics. And if you don't know, if the word hasn't got out yet, college courses are expensive. So if you could get a year of chemistry full fleet, that's a good deal. Or biology, or physics. General anatomy is general anatomy and physiology taught by Mr. Anderson. Not technically an AP class, but it's upper level class that will earn you credits at MWTC. And the AP Environmental Science is taught by Ms. Tutt. That's also indexed.
That's 1 semester.
For college credit? Okay, thank you. So AP Environmental and AP Physics are the equivalent of 1 semester of college credit. Chemistry and Biology, 1 year of college credit. We also have regular physics. It's a college prep course, but it's not indexed. It's not an AP class. It covers much of the same material, but not as in-depth as AP Physics 1. If you're debating between AP Physics 1 and physics, please come and ask me. I'll talk you through it and give you my suggestion. Intro to Physics isn't something that I think any of you should be considering, just because it's more of a introductory lower level class, maybe something to see if you're interested and want to pursue it further, but for the most part, the Intro to Physics and Intro to Chem, which you're definitely not taking, are to help those students that aren't all gung-ho about science, but still need science credits to graduate. Earth Science might be something you're interested in. That's a full year course, and that's taught by Mrs. Welsing. And then the last one, Basic Anatomy, is another full year course. That's 3 MWTC credits. That's also taught by Mr. Anderson. That is, I don't want to say it's a watered down, but it's a slightly lower level, less rigorous class than the general anatomy. Anybody have questions? Gentlemen, anything to add to that? Okay. All right, today's the 18th, tomorrow's the 19th, the day after that's the 20th. The 20th is the last day of the semester. Today your either or lab is due. The post lab is on the website if you haven't already done it. Just go to the website, either or lab, post lab link, click it. It's one question. You should write a good, healthy paragraph. 2 or 3 sentences. Probably not going to get you a big thumbs up from us, but also doesn't need to be a full page. All late work, homework, labs, tests, anything that hasn't been done yet needs to be done by 3 o'clock on Friday, or it's too late. All those that aren't done by 3 o'clock are going to turn into zeros. If you haven't taken the test from nomenclature, which was a week ago, it'll be 2 weeks ago on Monday, I think, then you've been dragging your feet, and it doesn't get any easier when you don't practice it, and then you go back and take a test. But in any case, if you haven't taken that nomenclature test, and I think there's about a dozen of you, you should have gotten an email today to say you've got a 0 in the grade book because you haven't taken that test. That 0 is going to stay a 0 if it's not done by 3 o'clock on Friday. Anything that you want to turn in, extra credit, homework, upload to Canvas, needs to be time-stamped by 3 o'clock on Friday. If it's 3:05, that sucks for you. Or Mr. Gussie likes chocolate chip cookies. Without nuts. He did have a student bring him chocolate chip cookies once. With nuts, walnuts. He's allergic. I am not allergic to walnuts. I'm not allergic to anything that I'm aware of. But
I had a itch moment in the movie. I actually was at Super Rounds opening up a Benadryl bottle, sucking it down in the middle of the aisle. It was awesome.
okay, that's all there is to tell you about that. So the last thing is to take a look at your homework. Since all right. I want that to get bigger. I don't know how to make it bigger. So it's not going to get bigger. Okay, on the front page of your homework, please write your name near the staple, upper right-hand corner. We didn't put a spot for your name. Please write your name. This is due on Tuesday, which is next semester. So instead of writing this semester's TOR and mod numbers, please double check your schedule quietly to find out who your second semester TOR is and what mod numbers. Just like this semester, it's going to be your Monday chemistry teacher and mod number. So I'll give you a moment to quietly do that. That didn't work. We're going to go through one of these examples together, and just to give you a little preview of what's going on here. As you can see by the article on the front page, a lot of you may not have heard about this, the Malaysian airplane crash, kind of took precedence over this one, bigger news than this one. But Mole Airlines flight crashed very recently because of Mole Airlines, yeah. Yep. Flight 10231. Is your grandma, I don't see her. She doesn't seem to be one of the primary suspects or individuals in this plane crash, but it's a murder mystery. That's what it is. It crashed not because someone was killed on the airplane, but because there was a bomb. Now we got to figure out both who got killed, by whom, with the help of whom, and who did the bombing. How are we going to do that? Forensic science, my friends, chemistry. So we got 16 pieces of evidence to collect. On the bottom of the page, on the front, gives you a short little bio of the 2, 4, 6, 8, 10, 11 or so primary folks. On the back page, there's a clipboard for your reference that gives the identity of possible compounds found on the scene. Gives the name, formula, and a brief little description. And we've got 16 little sticky notes that are going to be your pieces of evidence to put the pieces all together. We're going to do the first one together. You'll see that passenger A, we don't know who passenger A is. The passenger A has one sticky note, and the substance that we're going to determine was found in their blood. Passenger B has two pieces of evidence, two substances associated with them. Passenger F has three. A lot of them just have one. So we want to find out what substance was found in passenger A's blood. Let's get her done. So we're going to do what we just did. We've got the chemical composition, percent composition of this substance. 67.31% is carbon, 6.98% is hydrogen, etc. All those percentages add up to 100. So every time you see a percent sign here, we're just going to replace that with grams. Because our first step is to assume we've got 100 grams, and we're going to convert to moles. So our first one, 67.31 grams of carbon times 1 mole for every 12.01 grams. And I had this all figured out and left the sheet in my room. So if anybody wants to help me with calculations, that would be super sweet.
I can do that.
So for the first one, I got 5.604 moles. That's actually 604,49625. I could keep all those digits. I probably don't need to keep more than, say, 3 or 4. But please don't stop at just 1 or 2. Bless you. Likewise, with the molar masses, the atomic masses off the periodic table, at least go to 2 decimal places. The more decimal places you go to, the better your results are going to be on this homework. If you round this just to 12 and round your other ones to say 1 instead of 1.01 or 14 instead of 14.01, your results are not going to be good. And when it comes time to figure out what your formula is, you're going to be fighting an uphill battle. Okay, so we got moles of carbon. I need moles of hydrogen. Somebody can do moles of nitrogen for me. For 1 mole of nitrogen, we've got 14.01 grams. 1 mole of hydrogen, 1.01 grams. And oxygen, 16.00 grams. Who can hook me up with hydrogen?
I have 6.911.
Thank you. And anybody got a little nitrogen action for me? Perfect, thank you. Next, that's step 1. Step 2. Divide all by the smallest. So we're going to be dividing everything by 0.33. And actually 0.330. First one gives me 16.98, 18, which is really darn close to 17. 6.911 divided by 0.330 is 20.94242. Really close to 21. And it would be closer to 21 if we had carried more digits in here. This one I got in my head, 1. And lastly, 1.319 divided by 0.33 is 3.997. So that's 4. Those are all whole numbers already. So we don't have to come up with something to multiply them all by to get them as whole numbers. That would be step 3. Multiply to get whole numbers, if necessary. We don't have to. We already got them. So, our chemical formula is C17H21 NO4. I wrote that very poorly. Flip her over to the back. And you will find that passenger A, whoever he may be, is naughty boy. He's sassy. So 15 times more. What? You're asking the wrong guy.
Guys, if you find all 16, then you will need to figure out who's who. Don't make assumptions beforehand. You have to do them all first. Okay?
Oh, man.